Hi everyone, my name is Alex, actually Petrov, but I'm commonly called as Petrov, but it's okay, I kind of get used to it. So I'm working for the company called Instana. We're based in Germany. I live in Munich personally, and we're working on providing an intelligent solution in the monitoring space. So whenever the other solutions can't really say what's the problem because they haven't seen the problem just yet because they're not real time or they don't have enough intelligence to tell whether that's a problem or no. We can identify the problem and provide the solution and say like what exactly went wrong and how it could be improved. And we're trying to look at the data not as something that is disjoint. So we're trying to find underlying semantics behind the data and say and find the ways to provide the solution that will make sense out of the things like that are playing together. Majority of my spare time I spent working on the ClojureScript libraries, and Clojure is one of my favorite languages. It's extremely expressive and it's really easy to do many things that are pretty much impossible to do as interactively as in Clojure. So we have around 35 libraries, and we try to concentrate on documentation more than on the code, because we understand that if the people can't access the code, it doesn't really matter how good our code is. Therefore, like the documentation is the key to whatever we're doing. And a couple of words of introduction to the talk or to myself. First of all, I'm Ukrainian, and this is what it looks like these days to be Ukrainian. And this is my buddy. Like this particular photo was, well, the photo of this rocket was circling the internets, and some people were saying it's Gaza, some people were saying it's, well, Palestine and other places. But, well, I can confirm it's Ukraine, and everybody knows how good it is right now over there. And I also learned that many things have to be relearned over the course of the time. And the traditional educational system is giving you the set of knowledge which is so monolithic that you can't really fetch the data from your brain anymore. And you have to relearn everything, because if you want to take more holistic approach, meaning that you'd like to have more connections between the things and fetch them more easily, you have to, well, kind of extract them and put them over there once again. And I'd like to talk to the people and present them with the ideas, and in order to get to know what their opinion about the ideas are. Because it's impossible to know whether your idea is good or no until you bounce it off someone else's head. Because it may seem so brilliant and genius to you, but because you're missing the context, it's gonna not make sense for the other people. Or, well, the conference like that are very important to bring several worlds together and try to understand what is the optimal solution in a more general sphere. Whenever you're trying to get more expertise from the other technologies or stacks, you can actually provide the better solution. I had to fight a compiler a lot. I mean, whenever you're writing Haskell code, everybody, like, it is very well known to be fought with. But I also had to fight things like, I had to find the fact that even though Haskell has a tail call optimization, you can still face things like stack overflows. So, you have to optimize in very different ways whenever you're writing Haskell code, because like it's not a traditional language or not whatever you have seen in Java and C before. And I also had a very big pleasure to work with people like who wrote GHC. It's an amazing compiler, and even though I wrote like 2-line patches or two 2-line patches, it was an amazing experience, and it made me feel that GHC, so Glasgow Haskell compiler, is a compiler that I can very well trust, because the people are really reviewing your code and really trying to understand how it could influence their code base in the long run. So it's very, very promising for me. And whenever I talk to the people, I kind of feel like the status quo of the industry today is, well, pretty much like you see on the picture. So it's very hard to admit that even though we're trying to live in the future, many things are so distant and so, well, not existing, at least at the moment, that, well, it makes me upset. And as every developer, I'd like to live in a future where, well, every tool is up to date, is available, and, well, is working very well. But unfortunately, it doesn't happen very well, very often. And one of the problems I ran into is, well, the problem of the currently existing time series databases. And ever since I have started the research, it has improved a lot, and there are several systems which already provide at least, well, the working solution. Even though it could be improved and optimized a lot, it's still already like a huge step forward. And I'm not even sure whether the video is going to work. Yeah, it does. So basically, whenever you have time series data which is written to the database, you'd like to run the aggregates on the slices of data. So basically, you have a data set, you choose the collection, and then you choose the fields that you'd like to investigate or look into, and then you have several aggregates, and then you're trying to understand, okay, what your data is looking like. So the time series data is a little bit different from anything you traditionally write to your database, because the primary key of the time series data is monotonically increasing. So, well, time is mostly going forward. I mean, with the leap second, it's kind of like a little bit weird, but I mean, we can all survive that, right? So, but generally, the time is going forward, and therefore, our time series key, primary key, is monotonically increasing. And also, you cannot really say that, okay, this period in time in past has changed. Therefore, the data for the time series is write only. And in majority of cases, the type of queries that you're doing is the range query. So whenever you say that I'd like to know what happened between this and that period of time, and you'd like also to optimize by saving the intermediate results of your computation into some roll-up database in order to be able to access them faster without re-aggregating them all over and over again. And one of the best backends available for the time series data these days is the LevelDB. And there are several alternatives, but not all of them are matching, well, free and open source licensing terms. Therefore, well, LevelDB is kind of an optimum. And in order to work with LevelDB from Haskell, it was important to also, well, write quite a bit of the C code and also, well, do several, well, C-side optimizations. And it's also important to optimize the space and reads, which we're gonna talk about a bit later. For that, one has to understand the memory layout and understand the way which data is gonna be stored, and, well, understand how computers work, obviously. And in order to create the flexible aggregation system, you have to understand the algebras. And in order to parallelize the queries, you have to, well, come up with several solutions in order to, well, be able to know where the data sits and how to access it in a parallel manner. So in order to write a system which is successful, well, can successfully query or query-centered system, you have to start thinking about it from the querying perspective. Because whenever you start with a storage perspective, you may make several decisions which are going to influence your querying negatively. Therefore, if you start with the querying and you know that your queries have to be, well, going through the large amount of data, and you'd like them to be fast, you would like them to be also parallel, because, well, that's pretty much the only way you can optimize, right, over here. And in order to make the parallel queries on the time series data, you can split your query into 3 steps. The first step is just a local aggregate. So it's going to be running locally on some node or in some part of the of your database. And after that, the local aggregate results are going to be appended, so concatenated together, and then transferred to, well, coordinator node, and coordinator node will be combining all these results in order to, well, tell the user, the end user, what was the response for the query. And this, of course, is a little kind of simplification of the whole system, because, well, in order to do that, you have to implement, well, many things in between. And first of the things, like, is how do I even split the database in sensible chunks in order to be able to query them in parallel? And the key, or the first thing you can think about is the way you structure your keys. So the key is generally monotonically increasing, which is a timestamp, and the second part is going to be the sequence ID. So the sequence ID is, once again, monotonically increasing together with the timestamp, but well, not together, but it's rather independently monotonically increasing. So with each record which is being written into your database, the sequence ID is being incremented exactly once. And it could be used to avoid timestamp resolution collisions. For instance, whenever you have more than one data point per 1 millisecond, and at the same time you have only 1 millisecond resolution, you would have, well, overwritten keys, therefore you're gonna miss the data. That's what's happening with systems like Graphite, for instance. And you can also ensure the sub-resolution order together with the sequence ID. So you can say that, okay, these things were coming in that order, and even though they all fit into the 1 millisecond, they still have an internal order between them. And you can also use the sequence ID in order to say, okay, there were, for instance, 20,000 records between the last sequence ID and current sequence ID in order to, well, make a snapshot of the data. And you can also ensure idempotence. That means that whenever there are two writes occurred to the database which share the same sequence ID and same timestamp, they will not collide, so they will not duplicate the data, so they will, well, kind of override each other. And together with the sequence IDs, you can imagine the range table. So unfortunately, my pointer doesn't really work here, but like your keys are, once again, monotonically increasing. So you go like 1, 2, 3, it's like your timestamp is increasing. And then every 4 items, you're doing the snapshot. So you're going to be writing 4, 8, and 12 in that particular case into your snapshot database. So in order to perform the table scan, so full table scan from item 1 to item 13, you would have to perform several queries. First query is going to be run, fetch the items from 1 to 3. Second query will fetch from 4 to 7. Third one from 8 to 11. And the last one from 12 to 13. And all these queries can be run in parallel, and therefore, well, they can even be distributed across the several nodes. And this, well, can significantly improve the performance and throughput of the system. And the second type of the query is, of course, the open range. Whenever you know the start, but you'd like to read until the database end. So you start with 6 and want to would like to read until the 13. So you split it into the 3 chunks: 6 to 7, 8 to 11, 12 to 13. And once again, you read in these chunks in parallel. And the between range is, well, whenever you know the start and the end, and neither start nor end are the start and the end of the database itself, but rather, well, some range that you'd like to aggregate on. And you will, once again, split it up to the several chunks: 2 to 3, 4 to 7, and 8 to 10, and aggregate all those chunks in parallel. So that's already cool, because we already can take the data and split it into the chunks and, well, aggregate it. But that's not enough, because even though you can do the parallel queries, you can't really combine the queries in a sensible way. And you have to provide semantics in order to compose the querying system. And in order to help that, there is Stream Fusion. There is a really nice paper, Stream Fusion from list to streams to nothing at all, which I really recommend to read to anyone who's doing, well, stream programming or anything which is barely or even a little bit resembling the databases, because it's a nice concept which you can utilize in many, many cases. So the Stream Fusion is also implemented in LevelDB bindings for Haskell, and the basic idea behind the Stream Fusion is as follows. So you have a stream and a step. the step is either yielding the next item and preserving the state. In terms of level DB, the state is going to be just an iterator. Skip is just, well, bypassing the iterator without yielding the next item. And done indicates that, OK, there is no more state, and there are no more operations to be yielded, or no more items to be yielded. Therefore, we're done. And the, well, stream itself, it represents, you take an iterator and yield the step, so pretty much next step that you'd like to have. So basically, in terms of level DB, once again, it's going to be just 2 byte buffers. And you can start building on top of that abstraction, well, several other helpers in order to well, build the expressive query language. And the most straightforward thing, which is available in, well, pretty much every language that is existing right now, well, or we're getting there, is mapper. So the map is going to take the stream of A and, well, convert it or make it to the stream of B, commute it to the stream of B. And in order to do that, we have a function from A to B. And what we're doing is we're basically taking, if the stream is done, we say that, OK, we're done with the mapping. If we're skipping, so we're just bypassing skip operation. So we're saying, OK, skip operation is pretty much like we're doing pretty much whatever the underlying stream is doing. So we just skip once again. And yield is taking the x, so the current item which came to the stream, and it's applying the function to the stream and, well, yields the stream of B. And the same way you can implement the filter. And as you can see on the very bottom, we have this otherwise clause where instead of yielding the same stream, so we're kind of like changing the yield of x to s to skip of to s. So we're basically like, we had one type or data type or data constructor come into the stream, and we have changed it from, well, yield to skip. And this is pretty much meaning that whenever you're going to do collection, so very bottom of your aggregation chain, the item won't be present over there. And default is another favorite of every functional programmer. So you basically are accumulating the state recursively, and it's going to be, well, converted to some kind of an entity that you'd like to have. And the second, I'm sorry about that, clicked too much. And the second step after we have, well, combined, well, we have learned how to create, well, fusion streams in order to read the data from the database and convert it to some sensible way of, well, querying things. We have to come up with a set of operations in order to combine the data. And in order to combine the data, the best algebra that is available is, of course, a monoid. So monoid is basically a set with an identity operation and a binary operation. Together with the monoid, we should also have, well, some kind of a foldable or a fold, actually. So the fold will be consisting of a step, of an initial value, and a finalizer. The finalizer here may seem a little bit redundant, but because of the nature of the fold, you may want to aggregate in a way that is different from the data type which is going to be returned by the folder. And that also means that you can hide some implementation details within the thing. And the very last step is going to be just a combination. So it's going to take the appended monoids, and it's going to combine them to some representation. There are several examples. For the first and most simple one is, of course, a count. So count is basically constructed out of an integer. And in order to make a folding count or count fold, we're just ignoring the item that came in and accumulating or taking the or incrementing the state. So basically, if we had state of 0, we increment to 1, 1 to 2, and so on. The initial value is, of course, 0, and the data constructor, the finalizer, is count. So it's just a data constructor in Haskell. And now we have to implement the instance of monoid for the count, and the empty, so the constructor or initial value is going to be count of 0, and the appender, so basically the way to combine two counts is to summarize their, well, results. So count of 1 and count of 3 will yield, or when they're appended to each other, will yield a count of 4. And in order to combine or finalize the aggregate, we just say that, okay, if we had a count of, well, integer, some integer, we just yield the integer without a count. And the other example, because, well, count kind of, well, piped through several operations, so it didn't really utilize the whole system altogether. So the other example is, of course, the mean. The mean is implementable in several different ways, but this particular example is not using any, well, streaming mechanism for the mean. That means that we have to aggregate each and every item and then take a sum of them. So the operation of means, so the, well, the very, like, second and third lines are pretty much saying that we take an empty array and start appending the items to the empty array until we, well, reach the end. And then we combine arrays by simply concatenating them. And in order to calculate the actual mean, so, well, yield the result for the end user, we are, well, taking the length and the sum of these things, and, well, we yield the result. And the same way you can implement things like streaming histograms, because, well, streaming histograms are essentially monoids, and they are, well, they fit both in fold. So they are a concept very well fit into fold and into the monoid concepts. And you can calculate things like median. For that cause, you will just have to add the sorting into the combination operator. You can also calculate things like percentiles and you name it, whatever you'd like to have. And you can also do things like query combination. One of my favorite examples for combination is group by query. And group by query actually preserves all the properties of the underlying construct. So whenever you'd like to group things on a timestamp or on some timestamp rolled up to, or rounded up to some time period, for instance, up to 10 minutes, and you'd like to maybe group on a certain field, the key, which is either a rolled up timestamp or whatever the string you try to group on, is going to be kind of on the left side. And on the right side, you will still have the same exact monoid and false. So that means that you can do the group aggregates in a parallel in the same way as you've been doing any other simpler query without changing any semantics. So the groups are going to be working pretty much automatically with any type of the query which was mentioned beforehand. And you can actually do the nesting of queries well, as much as you want, because it's going to be preserving all the underlying semantics of each and every step. And other examples are, like, for instance, whenever you have to have several aggregates in a single run, you'd like to group by field or combination of the time and field, or have many nested aggregates, as I mentioned. And in order to recap, we, in order to have a flexible system, we try to break down the queries and calculate the queries in parallel. We aggregate each part independently, then we aggregate them together, and then transform the result in order to represent it for the user, or make it easier for user to read. But that's not the only way of optimizing. And the other way of optimization is, of course, the binary format. And for the time series database, it's very important to have a, well, good set of primitives, such as integers and, well, single and double precision floating point operators, and things like maybe strings and so on. And you represent a schema by, well, pretty much giving each field a name and a data type, pretty much like you do in any other database. And the layout of your memory is looking pretty much like that. So you have a header in which you specify the offsets for each and every field. Because, for instance, if the first field is a string, then and it's going to be of an arbitrary length, it means that you would have to know where the next field starts in order to calculate. So basically, you're going to have the offsets in a header, well, pretty much integers which are following each other, and you will have the memory layouted after that. So a chunk, pretty much like a payload, which is going to be offsetted for reads in order to, well, get the certain parts of the payload read out. And that means that you can actually read the parts of the payload without decoding an entire thing. And you can have the implicit field names, which means that you don't have to encode the field name or put it into the database each time you're doing write, and the same thing, you don't have to do it whenever you're reading things. And it also has several implications to the schema migrations, which means that like whenever you are doing the schema migration, you can, for instance, append fields, so add new fields, and they will be just appended to the end, but changing the previous records whenever you're removing some kind of a field would mean that you would have to go through all the records and, well, remove each one of them, or you can actually leave them in and just make them unavailable for reads. So, but that's kind of also an optimization question, and also maybe a legal question for some entities. So the very last thing I'd like to mention is the consensus, because consensus is the big thing everybody is talking about every day. And with the time series data, you can actually avoid having a consensus on each and every data point. Instead, you can do the consensus on the entire snapshot. So for instance, you can aggregate the data for a minute and then do the snapshot on the minute, and then calculate the CRC, ask the other nodes whether they agree that this chunk of data is stable across all the nodes, resolve the conflicts if it's necessary, and be done with it. It's also asynchronous. It means that whenever the data point is written to one server or to the several servers, it probably depends on the client demands. And it means that you don't have to wait for the consensus between the nodes, that they all agree that, well, the write is on the write itself. Then you can give the result to the client faster. And you don't need to have any quorum for the snapshot reads. That means that whenever the client is coming and making a read from the snapshot, you can be 100% sure that whichever node you're asking is going to yield you exactly the same result, because the data was already agreed upon. And you can also do the parallel reads from the snapshot data, which in the ways which we have already discussed before. And of course, writing a database is not an easy thing. And I'm not claiming that whatever I have written is either production ready or I would advise anyone to use it, at least at the point. And there are like companies which are, well, taking millions of venture capital and taking years and like 20, 30 engineers in order to write a successful database. And who am I to code an entire thing myself? So of course, this is just in a research work. And I, of course, had a certain amount of fun doing that. But unfortunately, I cannot say that up till date it's a production-ready thing. But the ideas are actually good. And we're using parts of them in the different systems that we're implementing. And if you want to have some fun, ping me up. We can actually collaborate on either this system or any other one which shares the same ideas. So the conclusions are use the more lightweight data format, do the partial decoding, optimize where you can, and try to make your query system more composable, and just think about the ways you're handling consensus on the data, because you may actually do lots of optimization on that thing. Also, I have my business cards if you'd like to ping me later on. And I have a couple of ClojureScript stickers laying here on the table. Just come over and pick one if you like what we're doing. And thank you a lot.
Well,
any questions? No questions.
Such a disappointment.
Disappointment.
Yeah.
So there's a lot of stuff you mentioned. So I imagine it's already implemented in some of the popular databases we use. And
You're gonna be surprised.
really?
Yeah.
I mean, I'm wondering, like, do you take into account some code that's been already in like different databases or something like that, or it's just a pure thing you start with from 0 to 0?
Well, of course, I mean, first of all, I didn't implement any storage myself. I've taken the level DB, but the database itself, I started from scratch. So there are certain concepts which are already used, but not every database, unfortunately, is using all sorts of these optimizations. Once again, especially the binary format is probably the most upsetting thing. Well, the consensus is another thing. Well, the query, once again, the parallel query is almost unimaginable. So, like, I know very, very few databases that actually allow doing parallel aggregate queries, so complex aggregate queries, mostly because of the nature of data. Once again, it's very hard to do the parallel queries unless you can do the sequential read, so it means that your keys are sorted in an incremental order already on the disk. And the second problem is that you cannot really take a range of data and you don't know where it sits, so you pretty much have to, well, go through like you have to know what the keys are at first and then do the second step. For instance, like React does it in with its like MapReduce JavaScript. Probably you've seen the GIF queries. But other than that, like there are no sync or very few synchronous query systems which are allowing such a flexibility and parallelism.
Once we're at the querying and so on, parallel querying, maybe I missed something, but